Hello again, time for physics. This is video lecture 19.2, and we're going to discuss two sections in chapter 19, both involving what is called the use of kinetic theory, which, remember, is part of the title of chapter 19. And I said at the very beginning of chapter 19, in the previous lecture, that kinetic theory is about understanding the properties of a gas, with a bunch of atoms and molecules moving around inside a container, by looking at the average behavior of its constituent atoms or molecules. And that's what we're going to start showing you here in this lecture. We'll start with section 3 in chapter 19, where we're going to relate the pressure of a gas, certainly something measurable with a pressure gauge, the temperature of a gas, measurable with a calibrated thermometer, and what's called RMS speed. Now that's already our first bit of technical jargon. RMS is an acronym where the R stands for root, as in square root. The M stands for mean, as in average. And the S stands for square, as in the exponent squared. And of course, speed means that property that we studied last semester, the magnitude of velocity. And if a particle is moving around in 3 dimensions, then its speed, the magnitude of its velocity vector, is square root of its x component of velocity squared plus its y component of velocity squared plus its z component of velocity squared. Okay? I mean, that's idea straight out of kinematics from Physics 110. And that's what the word speed means. Okay, so we're going to relate pressure and temperature to some kind of average measure of the speed of the atoms or molecules in the gas. So here's the scenario. The picture shows on the left a container, a box. It's got some volume V, which we just chose to be shaped like a cube, where each side is length L, so the volume is L cubed. And the box is kind of like an oven, where we can control the temperature of its walls. And the walls have some temperature T. And if we wait long enough, the gas will come to thermal equilibrium with the walls of the container, and so the gas will have temperature T. And of course, there are many gas atoms or molecules. We'll use the word molecule generically, zipping around inside this box. In fact, there are capital N total of these molecules. Our picture on the left shows one molecule, because amazingly enough, that's all we need to look at to start to get a feel for the pressure of this gas. After all, where does the pressure of the gas on the walls of the box come from? It comes from them bouncing off of the walls, colliding with, exerting a force on the walls. Okay. All right, so the picture shows one gas molecule with a mass m. Right, so that's the mass of one molecule. We've got to be careful that all the m's and n's are clear what they mean. That's what this m means. Notice this molecule has some particular velocity vector, v, at the moment we've taken this snapshot. And it's headed more or less towards the wall that's shaded there on the x-axis. And the little dashed line shows the normal perpendicular to the wall. So you can see what's going to happen. It's going to zip along, it's going to bounce off that shaded wall and then reverse and go back. Okay? We're going to ignore collisions of the molecules with each other for this calculation. And we assume that the molecular collisions with the walls are assumed to be elastic. The walls don't budge. And so all that happens in the collision then of a molecule with the wall is that the molecule, it reverses its direction. Okay? Reverses its velocity, I should say, without changing the magnitude of that velocity. That's what elastic means. Now, the net effect of all the molecular collisions with the walls is to exert an outward force on each wall. And the force per unit area is the pressure. All right, so to get a handle on that pressure, I need a handle on the force that the molecules are exerting on the wall when they collide. We know who to turn to in physics if we want to understand forces and their effects. Newton. Okay? So we're going to apply Newton's second law to a molecule's collision with the shaded wall. And I'll remind you of the form one of the forms we learned for Newton's second law. Might be a little bit of a blast from the past from last semester. The net force on an object, a particle, is equal to the rate of change of its linear momentum. That's what that little p is. Okay? So let's come all over here to the side. Okay? All right. dp dt, where that p is linear momentum. I'm going to apply that to our molecule. Okay? So what's going to happen is the molecule is going to come in, follow this straight line, it's going to collide somewhere roughly there, and then it's going to reverse the x component of its velocity, because that's the direction that's perpendicular to the wall's surface. Whereas the y component and the z component of whatever velocity the molecule had, unaffected by the collision with that shaded wall. So if the molecule had some v sub x coming into the wall, the effect of the collision is just to make have an x velocity the same amount going outward. And so what I'm going to do is I'm going to focus on just the x coordinate, f net x, and I can even approximate the derivative as delta p sub x over delta t. And the effect of the collision is to change the x velocity from v sub x to negative v sub x. Remember, momentum is mass times velocity as well. Let's not forget that. Okay, so if I say the incoming x velocity is vx, then the outgoing x velocity is negative vx. And delta px is px final minus px initial. So that'll be negative mvx minus mvx over delta t. So that'll be negative 2mvx over delta t. That'll be the x force on our molecule because of the collision. What I really want is the force on the wall. But Newton's third law tells me that the force on the molecule due to the wall is equal and opposite to the force on the wall due to the molecule. So the net x force on the wall is just plus. And then let's label that on wall. Okay? All right, now one more thing. Let me come over here to work a little more with that expression. How much time delta t? What I really want there is basically the time between two successive collisions of that molecule with the shaded wall. So the clock kind of starts when the molecule collides. It then goes over to the other side and then comes back to have another collision with the shaded wall. So what I want for that delta t is basically this is the average time it takes for this molecule to get back to this shaded wall. And along the x direction, that means it travels a distance 2L. And it travels that at a rate Vx. So the time it takes, the delta t, is 2L over Vx. How far did it go and how fast is it going? That's a very basic argument. Don't overthink it. Okay? This turns out to work very well, this simple argument. Now, you can see that things simplify a little bit. 2's cancel. And there's a Vx downstairs. It goes upstairs. So you get mvx squared over L. And that's one of the key steps we need. We need that result right there. Well, we got a lot of molecules hitting that shaded wall, exerting a force like this one right here that I just worked out. And it's the net effect of all those molecular collisions okay, that give us a total net force on the shaded wall. And if I divide that total net force by the area of the shaded wall, I'll get the pressure on the shaded wall. And that's what we're going to do right here. So now, warning, danger, danger, this little p symbol now stands for pressure. Okay, we're done with the momentum symbol, okay? Little p now means pressure. And so what this formula says to do is take the total x force from every one of the capital N molecules colliding with the shaded wall divided by the area of the shaded wall, L squared. So here comes the next line with that in mind. I take this expression right over here, and I have a contribution like that from every single one of the N molecules, and then I divide that by L squared. And this is how I get this next line for the pressure. So now I have out front an m over L squared, L cubed, because I have an L downstairs, and then I'm dividing by an L squared. And then inside parentheses, I'm just adding up the Vx squared value for every single one of the capital N molecules in the box. And we've just imagined that we can put a little number label on each molecule. Your number 1, your number 2, your number 3, all the way up through capital N. Every molecule gets a label, a number. So this says just take the Vx squared for molecule 1, plus the Vx squared for molecule 2, plus the Vx squared for molecule 3, and so forth, all the way through Vx squared for molecule N. All right, now, next thing, let me do a little explanation over here on this little box as an aside. I want to talk a minute about the word average, or mean. M-E-A-N is another word for average. Let's just take some generic symbol. I don't care what it stands for, Z, for some property of a system of particles. And I want to calculate the average value of this property. I'll label it Z sub AVG for this system of N particles. How would you calculate it? Just use the basic definition of average. Take the value of Z for every one of your N particles, add them up, and divide by how many there were, capital N. So take Z1 plus Z2 plus ... up through Zn, and divide by N. That's what we mean by average. So if I multiply both sides by capital N, then an equivalent way of saying this is capital N times Z average is just the sum of the N individual Z values. Okay? Just to rearrange that expression. Now I'm going to use that expression right there, where the Z, the property, the generic property of the molecule, is Vx squared. Just think of the Z as representing Vx squared. So what this equation right here, with the star by it, is telling me is take Vx squared 1 plus Vx squared 2 plus and so on, all the way up through Vx squared N, and that will be equal to N times the average value of Vx squared. So now I replace, we'll do a little erasing here. Now I replace that part right there in the pressure formula, the sum of the Vx squareds for the N molecules, with capital N times the average value of Vx squared. I mean, that's just what it's mathematically equivalent to. All right, so that's where we are so far. We're getting closer to a formula that's going to be useful. Just a little bit more discussion about what do these symbols mean. Think about that combination. Remember the symbols and their meanings. We've got to keep track of the M's and the N's. Little m, the mass of one molecule. I'm assuming, of course, that all N of these molecules have the same mass because they're the same species. Multiplied by capital N, the number of molecules. That's just got to represent, think about it, the total mass of the molecules in the gas. Right? Mass of each molecule times the number of molecules. Now there's another way to write that total mass of the gas. You have to think about this, and I told you you have to be careful about m's and n's. Let's look at that. Little m, mass of a molecule. Then just replace the total number of molecules, big N, with little n. Do you remember what that symbol means? The number of moles of the gas times big N sub A. Remember what that stands for? Avogadro's number, the number of molecules per mole, right? So that combination is just another way to write big N. Let's say it one more time in words. The total number of particles, big N, is equivalent to the number of moles of particles times the number of particles per mole. Okay, so we're going to replace big N with little n times Avogadro's number. So watch out, that'll be coming. All right, here comes another idea. This one takes a little while to get used to. All right, we have motion in 3 dimensions. So the magnitude of the velocity squared, v squared, from the Pythagorean theorem is v sub x squared plus v sub y squared plus v sub z squared for any one molecule. But when we average this expression over all the big N molecules total, then what you discover is that there's definitely nothing special about x direction compared to y or z. You have what's called isotropy, if you want to be fancy, in the gas. There's no special direction in space. There's nothing special about x versus y versus z. And don't worry about gravity, because you have molecules. They're microscopic in this calculation. We're not worrying about that. So there's nothing different between x, y, and z. So when you calculate the average value of, say, Vx squared, or the average value of Vy squared, or the average value of Vz squared for all these molecules, they come out to be the same. There can't be anything special about x compared to y or z. Okay? That's a very important idea. Big picture. Vx squared average is the same as Vy squared average, or equal to Vz squared average. Which means the average of the total speed squared is 3 times the average of any one of its components squared. In other words, V average squared equals 3 times Vx squared average. Or you could say 3 times Vy squared average or 3 times Vz squared average. We chose to look at that shaded wall that's on the x-axis. Now just rearrange that little formula right there. Vx squared average is the total the average of the total speed squared, and I ought to write that a little more carefully, divided by 3. I'll use the same notation I have over here. Take V squared and average it. All right, that just, again, it just boils down to the fact that all 3 directions are, look to the molecules of the gas equivalent. Okay, so let's put these various results together. So we're replacing big N that we had up above with little n times Avogadro's number. Remember, the little m is just the mass of an individual molecule. And there where we, up above, where we had Vx squared average, we now replace that with the average value of the total speed squared of the molecules over 3. And then we just use one more fact. The volume of the box, V, is L cubed in this case. So since there was an L cubed downstairs, now there's a V downstairs. All right, one more little bit of jargon. Now we define what's called the RMS speed of the gas molecules. And as I've said at the beginning of this video, RMS is an acronym for root, as in square root, mean, as in average, square, as in squared, speed. And this way we denote that is V subscript RMS. And all we do is, by its very definition, it is the square root, right there, of the average of the speed squared. Here's one case where the physicist actually came up with a name that accurately reflects what the thing is. It is the square root of the mean of the squares of the speeds of the molecules. Well, then this expression right up here, right there, is VRMS squared. So now we get this result. And that's the result that we want for the pressure of the gas. We won't necessarily use it a huge amount, but that's it. It tells me what determines what the pressure is of the gas on the walls of the box, or what determines that pressure. I do need to know the volume of the box, and the smaller the volume, the bigger the pressure will be. I guess that's because there'll be more collisions, right, with the walls, more frequently. I need to know the mass of the molecules, little m, and basically how many of them there are, and then the RMS squared speed, kind of how fast on average squared are they moving. But now we're going to rearrange this a little bit and get what we're actually going to end up getting is a formula for VRMS. Let me show you. Just take this formula, multiply both sides by 3 times the volume. You get that expression. Then divide both sides by little n times m and take the square root, and you get a formula for VRMS, right? Just rearrange and get a formula for VRMS. Then substitute our old friend, the ideal gas law. If P times V is equal to little n times the gas constant per mole, R, times the temperature. So you put the nRT right there. And then you discover that the little n's cancel. And you get a formula, and then this is the one that's pretty useful, and that's why I've got a box around it, for how you calculate the RMS speed of the molecules in an ideal gas. Okay? Now, we need one more thing, which I guess I didn't explain. I'm sorry for that. There's something else that happened between this step and this one. Just a little bit more counting. We took the combination of the mass of an individual molecule, little m, times Avogadro's number. So that's the mass of an individual molecule in grams or kilograms. And that's got units of per mole, because it's a number of molecules per mole. And that's going to be equal to, just based on the units, what your book would call the molar mass of the species of molecule in grams per mole. Okay? The main thing to remember about molar mass is that it comes from the periodic table. So that also happened, I beg your pardon there. And that then gives me that formula that has the box around it. And that's actually a useful thing, because that's a way to determine the RMS speed of the molecules of the gas. You need to know 2 things. What's the temperature T of the walls of the box, and therefore the temperature of the gas? And that's upstairs, so a higher temperature means a higher average speed for the molecules. And then big N is the molar mass of this species of molecule. That's downstairs, so the larger the molar mass of the molecules, the smaller the average speed. Right? Higher temperatures means greater average molecular speed, and larger molar mass means lower average molecular speeds. So let's look at a table from your book of RMS speeds, all at a temperature 300 Kelvin, room temperature for a warm room. Okay? The units of big M there in that column are that's the molar mass in 10 to the minus 3 kilograms per mole. I suppose you could say grams per mole, right? And the VRMS column is in meters per second. And it's got a number of the common gases that you will find in the atmosphere of Earth and in the rooms of our houses and buildings that we are in. And it gives the molar mass in grams per mole and the RMS speed in meters per second. And since they're all at the same temperature, the determining factor for why these various VRMSs are different is the different molar masses. And as the molar mass of the species of molecule goes up, the RMS speed goes down. The most massive molecule in this table, sulfur dioxide, at 64.1 grams per mole, at 300 Kelvin, the molecules have an average speed, RMS speed, of 342 meters per second. Already 342 meters per second seems pretty high. It's close to the speed of sound, right? Of sound waves in air. Then there's carbon dioxide and oxygen and nitrogen. As we go up, they get lesser molar mass, and the RMS speeds get larger. Now we're into the 400, 500, 600 meter per second on average. And then if you get to the really light gases, like the inert gas helium, with a molar mass of 4 grams per mole, look at the RMS speed for helium gas at 300 Kelvin. 1,370 meters per second. Wow, they're really moving. Or hydrogen gas, which is diatomic with 2 hydrogen atoms bonded together, molar mass of 2.02 grams per mole, 1,920 meters per second, moving along at a pretty good clip. In fact, this table gives you a little bit of a clue. It's just the beginning of the story, but it gives you a little bit of a clue as to why various planets that we have in our solar system with different masses and different gravitational field strengths have different gas constituents in their atmospheres. And it turns out that an Earth-sized planet, so Earth, Mars, Venus, so forth, with its gravitational field strength, it is not able to keep most of the hydrogen and helium atoms that might have been initially in its atmosphere. And so you're not going to find a huge amount of hydrogen and helium gas in Earth's atmosphere. Look how fast they're going, that's the point. But large planets, gas giants, like Jupiter and Saturn, for example, the 2 largest, have much higher, larger gravitational field strength. And they are able to trap even the fast-moving hydrogen and helium particles. Okay? So just this kinetic theory expression for the RMS speed of the molecules in an ideal gas starts to give the beginning of an understanding of the atmospheric makeup of the various planets. Okay, well, one more topic. Chapter 19, Section 4. Okay, let me bring that back down here, sorry. Section 4, translational kinetic energy. We got an expression for RMS speed. That's what you want to take away from the previous section, the formula for RMS speed. Although the formula for pressure that I mentioned, highlighted, is also sometimes useful. Now we want to talk about what's called translational kinetic energy. Now we studied kinetic energy last semester, and that's exactly the kind of kinetic energy we mean. The kinetic energy from the molecules just moving around inside the box. That kind of just basically straight line motion we call translation. Okay? So we're talking about the kinetic energy from the molecules moving along in straight lines until they bounce off the walls. We'd like to know what that value is. On average, because there are too many of them to worry about them individually. So here's the idea. Back to that picture of the volume V, the box, volume L cubed, focusing on one of the walls there, but that's just the picture redrawn. And so we're back to this picture of one molecule of a gas. But now we actually also allow for the fact that we know is true, that a molecule collides elastically with other molecules as well as with the walls. Certainly that is happening. Now, if it's a dilute gas, it doesn't happen, to a great extent, but it happens. And what happens when a molecule collides with another molecule, as opposed to the walls, which are immobile, is that the molecule speed can change. Now, the total kinetic energy of the two molecules that combine can't change, but the speed of each of them individually can change. So if you watch a given molecule over time, you can ask, what is its average kinetic energy over a certain amount of time? We don't need to keep track of each instant of the kinetic energy. It's fluctuating too rapidly. So watch it for some set amount of time and just ask, what's the kinetic energy over time? We'll call that the average kinetic energy of a molecule. K, capital K, symbol for kinetic energy, AVG. Take 1/2 mv squared, where v squared is the speed squared of the molecule. Watch that v squared and average it over time. That means sample its v squared at a bunch of different times and add them up and divide by how many there were. Okay? So that's what this means. Now, next comes a very important hypothesis that people at the research level in physics debate when it's applicable and so forth. But we will assume it's applicable for what we're going to look at. Here's what it says. The average squared speed of one molecule over time, averaged over time, is equal to the average squared speed of all n molecules at one instant. So watching one molecule over time is like looking at all n molecules at one instant in time. That's a pretty interesting idea. It's called, if you want to be fancy, the ergodic hypothesis. Ergodic. It's Latin. So we're going to replace the v squared time average in our formula for average kinetic energy with the v squared n average. Just pick a moment in time and say, freeze. And now go to each molecule, one by one, 1 through n, and say, what's your speed squared? What's your speed squared? What's your speed squared? Add them up and divide by n. That's the idea. But then use this concept of RMS speed that we just introduced, and you can say that v squared n average is just what we mean by RMS squared for the gas. So 1/2 times the mass of any one of the molecules, they're all the same mass, times the RMS speed squared for the gas. And then use our new result for VRMS squared. So it's 3 RT over big M, the molar mass. Okay. So substitute that for the VRMS squared right there. And you now get a 3 over a 2. Upstairs you have a little m, the mass of an individual molecule, the gas constant per mole, R, the molar mass, big M, downstairs, and a factor of temperature. And then again, just from the counting, the mass of one molecule is the molar mass in kilograms per mole, or grams per mole, divided by Avogadro's number, the number of molecules per mole. So replace little m with big M over Avogadro's number. You get some cancellation. Right there. 3/2 R over NA times T. And then from the previous lecture, you can replace the gas constant per mole over Avogadro's number with that other constant we introduced when we studied the ideal gas law, K sub B, which is called, I'll remind you, Boltzmann's constant. Excuse me, not Boltzmann's equation. There is something called Boltzmann's equation. Boltzmann's constant. Okay? And then you have a very simple result, amazingly simple, for the average translational kinetic energy of a gas molecule, or of the gas. Okay? 3/2 Boltzmann's constant times temperature. Okay? Average translational kinetic energy of a gas molecule. That's how we'll describe it. So what are some of the upshots here of that new result? Well, here's the tip. Here's one of the takeaways. At a given temperature, T, all ideal gas molecules, no matter what their mass, have the same average translational kinetic energy, namely 3/2 times Boltzmann's constant times the temperature. So it doesn't matter whether the gas molecules zipping around inside the box are hydrogen molecules, or nitrogen molecules, or oxygen molecules, or helium atoms. If the box has temperature T, then every one of those atoms has the same value for its average translational kinetic energy. The only thing that determines the average translational kinetic energy of atoms or molecules in a box is the temperature. So when you measure the temperature of a gas, you are in essence measuring the average translational kinetic energy of its molecules. So if we refer back briefly to the table that I showed you, table 19.3.1, which were some RMS speeds at a given temperature for different gases, notice then, if we asked you, because they do have, you can see they all have different RMS speeds, these gas molecules or atoms, how would their average kinetic energy values of the molecules compare? K average for these different species of gas. Did you say they'd all be equal? Because they're all at the same temperature, and that's all that determines the average translational kinetic energy. Okay, last thing I want to leave you with then is a class engagement exercise. So class engagement. On Blackboard with RMS speed and translational kinetic energy. That's what it's about. Here's the situation. We have a gas that is actually a mixture consisting of 3 types of molecules, type 1, type 2, and type 3. Okay? In thermal equilibrium at the same uniform temperature. They all are at the same temperature. And the masses of the individual molecules in the 3 types are arranged this way. The molecules of type 1 have the biggest mass, followed by the molecules of type 2, they have the next biggest mass, and the molecules of type 3 have the smallest mass. So, question A. Rank the 3 types according to the average translational kinetic energy, KAVG, largest to smallest, and then B. Rank the 3 types according to the RMS speed, VRMS, largest to smallest. So that's what you'll enter on Blackboard. Okay, so that is our discussion of kinetic theory. And we got expressions for the pressure of the gas, and the RMS speed of the molecules, and the average translational kinetic energy of each molecule. So that's all for this video.